Now, to understand why some materials are conductors and some are insulators and some are semiconductors, we need to talk a little more about their electron structure. So we're going to start by looking at copper. It's just a nice representative element. Here at this position in the periodic table, we know that it's filled the entire 1 level, the 2 level with both the s and p orbitals, the 3 levels s and p orbitals, and then it fills up the 2 4s levels, fills up the d's, and it turns out it's slightly advantageous to completely fill the d's and take 1 electron from the 4s. So the overall electron structure it has is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and then 1 in the 4s level. And that's what we have illustrated right here. We've got all the different levels just arranged sequentially. They're not really evenly spaced like this, but for our purposes, we don't need to worry about the spacing. We just need to know that each successive level is a little higher in energy than the previous one. And the 4s level is here at the very top. Now, in a crystal, the atoms get very close together, so that the outermost orbitals in particular start to overlap with each other. And just like inside an atom, electrons are indistinguishable one from another. So when the orbitals start to overlap, particularly when they start to overlap significantly, the electron in this one is no longer well defined to be different from the electron in this atom. They're indistinguishable from one another, and in fact they can trade places and go back and forth. What that means is that we can't have a separate state energy level for the electron on the left and on the right with the same energy. Instead, this 4s level becomes one single level for both atoms, but then it splits into 2 slightly different energies. They aren't very different, but this 4s level becomes one level for when the electron wave functions are symmetric, and another level for when they're antisymmetric, and those 2 levels are very slightly changed in energy. So it goes from 1 level to 2 very closely spaced levels. Then when we put in another atom, the 2 levels become 3, with another atom 4, 5, 6, 7, 8, until eventually we get to the point that we've got some macroscopic number of atoms. So if I have a full gram, it's going to be well over 10 to the 20 atoms. And each one of these energy levels changes into 10 to the 20 different energy levels. With that many energy levels, they're practically continuous. And we say that those individual energy levels that we saw before have changed from being individual single energy levels to being an entire band of available energy levels. Essentially, every energy within this band is taken. Now, if I look very closely, those bands are not completely continuous. There are separate energy levels inside them. But they are so closely spaced, and that spacing is so small compared to the thermal energy at any reasonable temperature, that for all intents and purposes, the energy levels are continuous within a band. Notice the uppermost band is the one that gets spread out the most, because that's where we have the most overlap between atoms. But all of the different energy levels show a certain amount of spread. And I would also like to mention that the energy, typical splitting energy, is on the order of Planck's constant times c divided by the length between adjacent atoms. So the one closest to it causes the biggest splitting, but because that's still much bigger than the size of the atoms, it's a much smaller splitting than the energy between gaps, the energy between the original levels in a single atom.